Good morning to one and all. A very warm welcome to 9th ISET Webinar by Professor Dipti Ranjan Sahoo on supplemental damping and energy dissipation devices. As usual, we received overwhelming response. More than 700 have registered to this webinar. We thank all the participants for registering and contributing to a noble cause. Today we have pleasure of having Professor T.G. Sitaram, President ISET and Director IIT Guwahati with us. Welcome you, sir. Now, I request Professor Sitaram for his welcome address. Sir, please.
Yeah, very good morning to all of you. Again, this ISET series has really taken online webinars to a new level. Okay, because every one of the lectures was well received, and large number of participants are participating, and there is a lot of interest in the earthquake-related topics. And anyway, I would like to thank at this time, our coordinators at ISET for making this very professionally conducted webinars. Today's talk is our supplemental damping and energy dissipation devices by Dr. Dipti Ranjan Sahoo, Associate Professor, IIT Delhi. I warmly welcome to this webinar. And also thank him for accepting to deliver this talk on this ISET webinar series. I will just take few minutes of your time to bring in some of the important announcements of the ISET, Indian Society for Earthquake Technology. Anyway, before that, so tomorrow is the 6th International Yoga Day, and this time all this International Yoga Day is conducted virtually. The theme of this year's Yoga Day is Ghar Ghar Mein Yog. That's a very beautiful statement. Okay? You have to do the yoga with the family. Okay? So this has happened to be 21st June 2020, which is the 6th in the series since the Honorable Prime Minister declared International Yoga Day and accepted by very large number of countries in the United Nations. Coming to the next item, the ICRAG. I think again I thank the organizers and ISET committee for working very hard on the 7th ICRAG to be held in Bangalore. It was supposed to be on 13 to 16 July 2020. All of you, I hope, know, mark your calendar. It is now 12th to 15th of July 2021. It will be in Indian Institute of Science, Bangalore, and at the J.N. Tata Auditorium. I request all of you to see the website, and I also request the organizers to change the brochure's date also. See, they have put in the front. Maybe you have to also change the brochure's dates and also give a statement of the account, how many keynotes and other things are already been received. See, we have received more than 70 speakers who's going to speak there. And we have received more than 400 or 450, I think, abstracts. All this detail anyway, it will be uploaded in the website. And there are more than 25 international speakers. So that's a very attractive about this ICRAG, 7th ICRAG to be held in Bangalore. I request all of you to look at the website. That is the ICRAG. If you just simply type 7th ICRAG, it will appear in Google. Please join us in July 2021. So we request all of your support and cooperation in this organizing this conference. I would like to happily to tell you, thanks to again the volunteers who are working hard, the proceedings are getting ready. Both the keynote volume as well as the contributory paper, first one. Okay, the second one will come maybe later during the conference time. First one will appear. Both will be coming in the Springer journal series. Okay, one will be a Springer book series, that is the keynote volume. The other one will be the civil engineering series, which is also getting ready. So with this information on the ICRAG, I would like to move now to the World Conference on Earthquake Engineering. The International Association for Earthquake Engineering, IAEE, has actually invited us, and we had shown an interest of contributing. are organizing the 18th World Conference of Earthquake Engineering in India. That's going to be in 2024. Please remember, this is 2024. So our email was sent, and suddenly, the conference, even the 17th conference, supposed to be in the September of 2020, it got postponed to the next year. That is the 17th World Congress on Earthquake Engineering, which is being held in Japan. Okay, so that is also postponed to next year. But however, the proposed time frame, I would like to bring it to all your notice just for the information. And June 15th, IAEE already has sent an instruction to all of us. That means June 15th is just about 4 days or 5 days back. So we got the instructions for online bidding and voting of the candidate sites. Okay, there are 5 countries which are participating in the bidding. And September 30th, we need to submit all the documents to ISET. Why I am telling all of you is it also reminds us to work hard, and also reminds our volunteers to work hard to note down the deadlines. Sometimes, in the email, we miss it. So September 30th, we need to submit the bid materials to IAEE. And then October 15th, the candidates have to make a presentation of the video messages. And this time, everything is online. Note that's very interesting. And then IAEE will also pose some question to us by sometime in October. And then they will all post that online. And then November, the voting will happen between 13th to 18th. They have given 1 week for the member countries of IAEE to vote which country they would like to have host the 18th World Conference on Earthquake Engineering in 2024. November 25th of 2020, they're going to make an announcement on the bidding process. So just to brief you, Ravi has already done a fantastic job, prepared the letter, and we have written to Secretary MOES and also the Minister. We have received Honorable Minister of Science and Technology the message saying that he is going to support our event. Similarly, we have requested Honorable Secretary also of Earth Sciences, and I have also written to Honorable Minister for HRD to support this event. And it is going to be in Delhi. The venue is also going to be decided. It's going to be in Delhi. We have to work now on the video and the publicity material, and also contacting all the member countries. We are going to begin that with all your support. Okay, we need some money, but we don't wait for that money. We are going to go ahead and do that ourselves. Let us see. But we would like to have the support so that we can do it much more elegantly and professionally. So last, Ravi, I have taken a little more time, and I also say, Sahoo, I'm taking away 2 minutes of your time, but I would like to talk about a little bit about the earthquakes in Delhi. See, all of you have seen, and many of you, actually, Sahoo and other people are all from Delhi, they're all worried. So more than 10 earthquakes, mostly at most 13 earthquakes, have caused panic in Delhi. Knowing the seismicity history of Delhi, and myself and many of our students, even recent PhD thesis of Ramakrishnan and Mona Lisa, also addressed the seismic hazard of Delhi region only. And I was also part of review team along with Professor Arya. Arya was our chairman to review the seismic macrozonation of Delhi NCR, which was conducted. So I was part of that. Knowing the seismic history of Delhi, the occurrence of minor earthquakes in the vicinity of Delhi is not a very unusual phenomenon. Please, don't panic. It is not a very unusual phenomenon. It is happening. If you simply Google it, you will find so many papers indicating this small magnitude earthquakes occurring in Delhi. The seismotectonics of the Delhi region indicates the presence of several lineaments and faults in the region. That is, there are many faults and lineaments in this region, which are responsible for earthquake activity, present earthquake activity in this region. The outcrops of Alwar quartzites in South Delhi are generally highly jointed and folded. So they can also yield because the Indian plate is not a very rigid plate. It is also moving. It is moving at the rate of almost 5 centimeters per every year in the north-northeast direction. Some activity near the junction of Delhi-Haridwar Ridge also was noticed earlier, and the Lahore-Delhi Ridge also. So most of this area of Delhi please understand, 3/4 of Delhi is covered with alluvium because of Yamuna River, which is again related to the site effects. That is where the geotechnical engineer's roles is important. What I would like to tell you is, please remember, this seismic activity is known only. This is caused panic because many people are telling different stories. That's why I'm taking time as the president of ISET to at least tell a small group of people who are here, about 350 now, to tell them that no need to panic. The area around Delhi is experiencing a series of earthquakes of mild intensity for a long time. It is not a new phenomenon. Earthquakes happen in around Delhi, NCR, because of its several fault lines. Maybe lockdown may have an impact. Please understand. Maybe lockdown have an impact on the people who are mostly at home now, to feel the more threat of these vibrations. Earlier, they were always moving around and they were never bothered. So now large section of people are noticing it, and that is also causing a fear. Due to this movement, see, also note that Indian plate, as I told you, currently moving northeast, in the northeast direction at 5 centimeters per year. Due to this movement, the intra-fault lines, what I've talked about, the faults and lineaments around Delhi, are subjected to movements, and these shocks are very common. You don't need to be frightened about it. Most of these shocks are shallow focus and very small intensity, with only one earthquake occurred at Rohtak was above 4. Please note that, which falls under the medium intensity quake. Also note the nearest point from the main boundary thrust. See, we are, one more thing, we are very close to, Delhi is very close to the main boundary thrust. That is the plate boundary between the Eurasian plate and the Indo-Australian plate. So this plate boundary thrust is only about 180 kilometers away from Delhi, okay, in the range of about 200 kilometers. So MBT is a plate boundary on which large earthquakes can occur, but it does not happen. There are a lot of gaps, seismic gaps there, but that can occur anywhere, anything like any of the interplate boundaries. So the Himalayas is known for very high seismic activities. So when it shears there in the plate boundary, the shock may travel to Delhi and can cause damages. So even the Nepal earthquake, you have seen that. So if any quake occurs in Himalayas or even in Hindu Kush, the impact could be on Delhi NCR. In 2015 Nepal earthquake, which was felt across the Indo-Gangetic belt, including Delhi, is one such example. That means people are asking whether Delhi can attract a large earthquake. Definitely not from these local earthquakes. But there could be an earthquake in the plate boundary which can hit bigger. Okay, and also with site amplification. That means answer has to be understood very clearly. It is more of the large earthquakes which can happen on the plate boundary with the soil effect can have a larger impact on Delhi, but not this. These swarm of activities of the earthquakes can cause a bigger earthquake. So there is a clear distinction between the two things that has to be brought out. That is the reason I took time today to explain to you. Delhi lies in the Indo-Gangetic belt, which has sediments. These sediments amplify the earthquake motion, and the role of geotechnical engineering is very, very key to understand this. And thus its impact is much more. So no one can say when earthquakes can happen. So even science of prediction is not there. But however, it is not possible to predict earthquake. However, the science of prediction has not progressed much also. But it doesn't matter really. But what is that required? So then the collision between Indo-Australian plate and the Eurasian plate in the northern and northeastern part of India makes it more vulnerable to hazards. So that has to be kept in mind. So Delhi is vulnerable to earthquakes. When there are natural hazards, they cannot be prevented. So these natural hazards are termed as disasters when they occur in places that are heavily inhabited areas, like Delhi. So disaster risks in India are further compounded by increasing vulnerabilities related to high population density, changing demographics, and construction quality. The main reason for India being more prone to so many of the serious effects and scale of these disasters is because of the high density of population and also poor construction quality of our habitat or buildings. So it is not that India only faces a large number of disasters. and many countries face more disaster than we do. It is not just here I have only isolated. There are many other countries are also facing a lot of disaster. But India's population and density of urban areas are the major reason. And it is much more severe now because most of them are staying at home. When they are staying in their home, as I told you earlier, earthquakes don't kill people. It is the buildings. So the buildings, if it is not engineered and they are weak, subjected to these earthquakes, can cause large number of people, deaths because they are at home now. Most of them, because of the lockdown, they are at home. So earthquakes, so the quality of construction plays a major role in deciding this factor. So people also try to compare with Gujarat because same time a Gujarat earthquake also happened. Please remember, Gujarat earthquake is not a interplate earthquake. It is intraplate, one fault is moving. It is not the Gujarat earthquake cannot go up to 8, 9 magnitude. Okay, it will be in the range of 7 because it is the sharing. So, and also Gujarat, so people are saying Gujarat is studied very well and all the geotechnical details are done. Yes, definitely when Gujarat happened, we all woke up and started doing a lot of activities. So done, but it is not that nothing is done at Delhi. Delhi also has been mapped very well through seismic microresolution, thanks to the government of India. They have done a fantastic job at a scale of 1:10,000 at seismic microresolution map. But not that now that should be put to use by the administrators. We have to use them appropriately. So this microresolution maps, which are available to us at a very refined scale with very serious science things going on, so can actually help us. So we need to take up immediately the restoration or retrofitting of hospitals, schools, and important buildings. And we should make sure that this, but technology of retrofitting is not very great. Most of our structural engineering can handle. And today, Dr. Sahoo will also highlight some of those, how, when you are building a new buildings, what to be done for particularly very important buildings. He's going to highlight through damping and energy dissipation devices. So the solution lies in understanding, solution for these earthquakes lies in understanding our building subjected to earthquakes, subjected to earthquakes, not really earthquakes. So that means we need to understand, see, as we know that, most of our structures are not concrete structures. Our concrete structures are maybe about 5%. Majority of them are with clay, mud, stone, all kinds of those. So the different typologies and different shape structures, we should understand how these structures behave when they're subjected to earthquakes. It is not really the earthquake we need to study. So it is important to put an emphasis on sensitizing people and taking precautionary measures. There is a strong need to prepare the community for earthquake disaster. Earthquakes, the awareness of the earthquake resistant design, the awareness of earthquake resistant design and earthquake preparedness are the two important to the whole country, and particularly so in Delhi. So if disaster strikes, how well prepared we are, we can ask a question. Earthquake preparedness is not part of the public consciousness, even in the vulnerable regions of India. So we need to do a lot of work there. There are many things that individuals and communities residing in seismically active regions can do and reduce the havoc and loss during a quake. So these steps can be a complementary measure alongside other activities that focus on the overall development of the community with a team spirit. There is a need to bring the spirit of togetherness and solidarity well before a disaster so that a community can be prepared well to face the disaster and thus reduce the loss of life and properties. India's preparedness, as we all know, that is poor, and we have actually covered that extensively. Myself and Dr. Srivalsa has covered that extensively in our book, Preparing for Earthquakes, Lessons for India. It's a Springer book, or some of you can download from the website. It's already well downloaded by many people, large numbers. Srivalsa will give you the numbers later. And we highlight actually how well prepared our community is. We have even done a survey. The primary goals of these books are to invoke alertness and solidarity among the people in earthquake-prone areas of India and to empower the community to prepare themselves to face and manage the aftermath of an earthquake. The work presented in this book sheds new light on the action plans to be taken by the common public and minimize the loss of assets. This carefully presented book articulates various factors related to relevant stakeholders. The book has been divided basically into 3 parts. The first part providing background which explains the earthquakes in general and seismicity of India. Second, explores the earthquake preparedness intended for individuals, families, and various stakeholders. And the third part describes the various strategies for communities to prepare themselves for a future. So with this, I would like to say that you don't need to panic in Delhi. Please, take care of, and I think ISET also should do more activities, and we will do. I'll assure you, we will do more activities to bring community awareness. Sir, these kind of guidelines are plenty. It is not that you have to only follow our book. Plenty online. What is important is the education and making aware of the people is very critical. With these few remarks, I welcome Dr. Dipti Ranjan Sahoo to deliver his talk on supplemental damping and energy dissipation devices. Thank you very much. Have a great day.
Yes, thank you, sir. Thank you for highlighting not only various activities of ISET, but also addressing ongoing seismic activity in India. And you, as a president of ISET, you clarified many aspects and doubts in the mind of common people. And in fact, it sets the perfect platform for Dr. Sahu to start his presentation. Before he starts the presentation, I would like to briefly introduce about him. Dr. Dipti Ranjan Sahoo is currently working as Associate Professor in the Department of Civil Engineering, Indian Institute of Technology, Delhi. His research interests include the hybrid testing and simulation, performance-based seismic design, development of passive vibration control devices, nonlinear modeling of structures, and seismic retrofitting and strengthening of structures. He is a fellow of Institution of Engineers, India, and a member of American Concrete Institute, Earthquake Engineering Research Institute, EERA, and also he is a member, and he served as past EC member of Indian Society of Earthquake Technology. He has also served ISET as associate editor. He is a very active member. He is a member of several expert committees, particularly committees of Bureau of Indian Standards, and he is currently working member of IS 458 revisions committee. With this brief introduction, I request Dr. Sahu to start the presentation. And just a small announcement to all the participants: please mute all the time your mics and don't turn on video, which helps to improve the quality of video streaming. And as usual, we will be taking attendance at the end of the lecture, and question and answers also at the end. We will enable the chat at the end of the presentation. With this, I am handovering the session to Professor Sahu. Please, Professor Sahu.
Hi, Professor Jakas. Thank you so much for the nice introduction. Professor Sitaramji, Professor Matsagar, Professor Sivasa, and my friends. So, good morning. Today's presentation is on the supplemental damping and energy dissipation devices. This is the 9th lecture of ISET Webinar series. I must thank the Indian Society of Earthquake Technology for giving me a privilege to explain the basics of the passive devices and how they are used in earthquake resistance applications. So today's lecture, essentially I will focus on the basics of what is damping and what is energy dissipation. What are the devices are available currently? So I have taken from the literature. And what are the devices we are actually working at IIT Delhi? Their potential applications, and one of the case study on retrofitting and strengthening. So as you know that, earthquake, it essentially starts along the fault when there is a rupture of the rock, and that fault rupture, it essentially dissipate the energy from that location, which we call as the focus. And from that, the waves are either the body waves or the surface waves. So these waves essentially consist of the energy, which, very, very high energy depending on earthquake magnitude. It comes to your ground surface or the, earth surface where your structures are located. So due to this earthquake, events, due to these earthquake events, actually, so there will be, you have a source where the earthquake actually happens, and then it transmits through the soil based on the surface of the body waves. It reaches to your structures, maybe buildings or bridges or dams. And sometimes based on your site conditions, like your soft soils, like the amplification of the energy or the wave may occur. Now, if I see that like this is the location site where there are some buildings or bridges or the dams are there, the earthquake energy or the excitation actually is not always parallel to the building or the perpendicular. It is inclined to the normal direction or the vertical direction and the horizontal direction. So mostly what we actually do is we actually, take their components in two orthogonal direction in the horizontal direction, X and Y, and the vertical directions. Now, if so, mostly the vertical earthquakes are, or the component of the vertical earthquake is smaller than the horizontal earthquakes. So in many applications, the vertical earthquake effects are not considered, but yes, there are some cases where you have to take the vertical earthquake component. So if you have, let's say, a building and you have some in one direction out of the two orthogonal direction, you have one direction earthquake, let's say I'm saying X component, which is acting at the base. Again, it may be amplified or de-amplified based on the site conditions. So when you have the earthquake ground accelerations, depending on the stiffness of the structure, it actually transmits from your base to your floor levels, or you can say the superstructure levels. And you have your superstructures or the floor levels where you have the mass as there. So M1, M2, M3 are the masses. And so at each floor level, again, these earthquakes are, it might be, nearly similar to ground acceleration, might be smaller than that, but they won't be same. Again, it all depends on the stiffness of the structure. So let's say at each floor level, some earthquake is A1, A2, A3. There are some earthquake acceleration components. These acceleration times the corresponding mass creates the forces, and we call it the equivalent lateral forces due to earthquakes. When these forces are actually act at the floor levels, your structure deflects, and the deflection will vary from the base to the free part, like delta 1, delta 2, delta 3. So if I just simplify the problem, like let's say I have a single degree of freedom system, that is one mass concentrated here and supported by some system with stiffness K. So if I have a lateral force F is acting and is acting in a monotonic direction, that is, let's say, in one direction only, towards the right. So you have the displacement delta, and this displacement delta will, if you increase this force, your delta will increase. Now, if I try to actually measure the force versus displacement, like what is I apply some force and I measure the displacement. And if the system is totally elastic, that means if I release the force, the structure will come back to its original position. So I will get a force displacement relationship, which is linear. So that means if my loading is this is my loading path. So my unloading path will be same. And so when I release my load, so it will come back to the origin. However, like due to this force at any force level, I have displacement. And if I take that area of this curve, force displacement curve, that gives my energy. But since this energy, like the forces, you release the force, your displacement is zero. This energy we call as the energy, recoverable energy or the elastic energy. Mostly you have used, it's called the strain energy you have used in many applications. So if I actually change little bit to earthquake load, so that means you have force and you have the delta, positive delta and negative delta, but the structure is again linear, so you will get the similar curve, but it has a tension component and it has a compression component, like the push and pull component. But again, once you release the force, it will come back to position, so it is called as the recoverable energy. And this energy is the structure is absorbing when you are applying the applied earthquake force. Now, if I go to a little inelastic system, that means your structure is not elastic, so it is elastic up to some point, and after that you have a non-linearity in the structure. So what, again, you apply the monotonic loading. So what you will see that you have a linear portion here in the force different behavior. And after that, your stiffness changes, right? So it's called the non-linear system or the inelastic system. So if you see that the point where your stiffness changes, it might be due to cracking in the concrete or maybe the yielding of the steel. But when you are in the second segment where your stiffness is smaller than the initial stiffness, if you try to unload the structure, it will not come back to its origin. It will have some kind of permanent deformation. So that means you will not recover your structure to a initial position. So the energy which is shaded in this portion, the right side part, is called the non-recoverable energy, or we essentially call as the energy dissipated due to damage. Okay, so if you have a structure where you have some, let this force represents some kind of earthquake energy, and so that earthquake input energy. Now, if you have a structure which is capable of giving this kind of behavior, so if your energy dissipation capacity of the structure is higher than the input energy, your structure will be safe. It will not collapse. Now, if your force is too much, is beyond your capacity of the structure. See, remember that in your practical structure, you don't have unlimited inelastic deformation. For example, if you simply take a mild steel bar and put it in the UTM and apply the tension loading, you know that like after some time, some strain, the bar will rupture or the fracture. So it may be 20%, 23% depending on the grade of steel. Similarly, like each material, they have their limiting strain capacity. So if I see in that point of view, like you have a limited deformation capacity which your structure can sustain. So up to that capacity, if your energy, you can calculate that shaded area. If that energy is higher than the input energy, your structure remains safe. But in case your energy capacity is smaller than the input energy, so you have the failure of the structure. Now, again, the similar inelastic system, I am going to earthquake loading. Now, when you have the earthquake loading, your structure will vibrate to left and right. And then if again you have inelastic system, so initial part is elastic, then you go to the inelastic zone. And so then when you do the unloading, so it will follow this path. And then in the compression, again, you have the yielding or cracking, and then you will get this kind of curve, which is relatively like, looks like a parallelogram. It's very, very, simple modeling or, it's a very simplification, but in actual structure, you may have or you should have the highly nonlinear structure. So that means it's not a parallelogram, it will be some kind of nonlinear curve, not the two straight lines. I'll show that in subsequent slides. So what essentially it shows the energy dissipated in this area or the area under this curve is called as non-recoverable energy, and we call as the hysteretic energy. Hysteretic means the energy which is essentially like due to the cyclic like tension and compression loading. Okay. So from the simple system, I'm coming to a physical or realistic structure. So you know that the simple structure is your beam. You have done some kind of analysis, many analysis on the simply supported beam. The beam can carry the axial load, so that the lateral load. It can be UDL, it can be point load, triangular loading. When the same member carries the axial component, we call as the column. In general, like a member carrying the axial load and bending, we call as the beam column. But if I take a simple, any generalized structure or generalized beam, we can say. So one can, depending on the boundary conditions and the loading, one can do the structural analysis, can get the bending moment diagram, can get the shear force diagram. Now, forget about the bending moment diagram. Now, the shear force, when you have this kind of force, you can calculate the shear at each level. So when you apply this force, you have some displacement. So that means I can plot my shear versus the displacement. Okay. Now, if it is a linear system, it will be similar to what I have showed here. You have the linear behavior. Now, so if your x-axis is shear and y-axis is the corresponding shear displacement, it also the area is also the energy. Now, if I come to the bending moment, so I have the bending moment at some points, and if I try to find out the corresponding rotation, moment versus rotation, so if you take the product of the moment and rotation or moment and curvature, it is also some form of the energy. Okay, so when you apply, do a beam test, so what you find is like your beam may fail in flexure, or that is called the flexion failure when you have some ductility, or you may have the shear failure, which is relatively non-ductile or brittle element. So in realistic structure, your beams, columns are not purely elastic. So they go to their inelastic structure because the material we use, they have limited in elasticity. For example, the steel rebars in the concrete members, they have a particular yield point. Similarly, the concrete has some cracking strength and ultimate strength. So realistically, like in any beam or columns, when you apply some kind of loading, so they will behave as a flexural member, or the flexural behavior you can get the shear behavior. So if I plot the moment versus rotation curve, or shear versus the displacement curve, or axial force versus axial displacement curve, I will get similar behavior like this. So this is also some form of energy you are actually, either it is absorbed by the member, if it is elastic, if it is inelastic. So what you can get is like, you get the damage in the structure, like, it can be concrete structure or steel structure. In steel, the damage we call as the yielding, in the concrete we call as the cracking. So what happens, like, if you once the structure damaged and you still apply the load, there will be a particular section or region where the bending moment will be maximum. Then you say that, like, bending moment is maximum when it reaches the plastic moment capacity. You do the plastic analysis. So if I put it in that form, like this moment, the rotation curve or the shear displacement curve, so what you can see is like you have a yield point, you have ultimate point, and then you have post or ultimate the degradation. So whether it is a flexure, like you have sufficient ductility that is beyond elastic, or it's a shear, so some amount of energy is actually dissipated in elastic structure. So with this as the background, now how we use it in earthquake design. When you go to the seismic design philosophy, or the kind of seismic design philosophy you adopt. Now, if we say that for a given earthquake design demand, my structure has to be linear. So that means, let's say this is my total resistance of the or resisting force of the structure in the y-axis, and in the x-axis, let's say some kind of displacement, maybe in the roof displacement. So if my structure has to be linearly elastic, so this is the curve I should expect. Let's say this is the point corresponding to the earthquake energy demand. Okay, now so this is the force I should design. But if you take this force, what you will get that your member sizes, beams and columns, will be very, very heavy. So in financially it is not possible. And the second point is like, why should I design my structure when I know that I have a material which can go to the nonlinear range without collapse? That means you have a yield, then it reaches the ultimate. So your ultimate strength is higher than your yield strength. After you reach the ultimate, you have a collapse or the failure. So if I know that like this kind of strength reserve capacity I have, I can utilize the inelastic portion in my design. So we have a ductility, that is your maximum displacement to the yield displacement, you can define that. Then you have some overstrength in the that is ultimate to your, let's say, yield, or in most of the cases, if you take a specified yield strength of, let's say, mild steel, 250 MPa. So actually what you will get that when you do the test, the steel yield stress will be higher than 250. So that is also called as the overstrength. The third point is, if we connect all these members, like the structure I have shown here, so you have beams and columns, you have the joints, you have the fixity. They also provide additional resistance to the structures. That is called the redundancy. When we know that these three components are there, so what we do is, instead of designing my structure to remain elastic, we allow the structure to go in elastic zone. That means you go beyond the yield point, but you would allow the limited damage in the structure. So if you do a kind of a plastic analysis, so depending on the capacity of the beams and columns, there will be plastic hinges in the structure. So that means you have a structure, you apply some increasingly lateral forces, you will get the plastic hinges in the structure. So what essentially my point is, in the current seismic design philosophy we adopt in the practice, it allows the structure to be damaged. So when you say that the structure, the members to be damaged, that means the members can come back to its original position. So once your beams and columns are damaged, essentially, let's say, this is the example, like when you have some cracking in the beams or the failure of the some members, that means although the structure is standing in a tilted positions, your beams and columns are actually already damaged. So you have to retrofit those structures, the members. And so if you retrofit, that means without retrofit, probably in many cases, it's not possible to use those beams and columns of the entire structure. So if you don't want that your damage to be very, very high, or there should not be any damage in the beams and columns, you need to have some additional elements fitted in this structure. Okay, and that we call as the supplemental devices or supplemental components. So essentially, for a building, for example, you need only the beams and columns. These are the primary components. Now, what you are going to do is, you want to reduce the demand, you want to reduce the damage in the beams and columns. So you need something else to support that. Okay, so that's why they are called as the supplemental systems. Okay, and the idea of the whole essence of this concept is, the total energy being applied to this structure now will be shared by not only the beams and columns through flexion cracking or the shear or the axial deformation, but also due to supplemental devices. Now, remember that the supplemental devices, if we don't have supplemental devices or the additional devices, my structure is okay. It is perfectly fine standing tall. There is no stability issue. So in many cases, not in all cases, in many cases, supplemental devices are designed to fail first. That means it should damage before your beams and columns should damage, because that is the essentially the motto is, right? Because I can simply remove the probably like these supplemental devices and without disturbing the stability of the entire structure. Okay, so that is essentially it's called as the energy dissipation or the energy balance concept. The total energy being applied, input energy, must be dissipated by some hysteretic manner, like by damaging the beams and columns, or maybe in the supplemental devices or the passive devices. Now the second term is the damping. So essentially, like your damping is a resistance to the motion of a vibrating body. Like if you take a structure, and let's say cantilever structure, or simply to take a rod, fix it at the ground and pull it from the free end and to some displacement and release. So essentially you'll see it will vibrate, and that rod will come to a zero position if automatically. That means vibration, there is a degradation, reduction in the vibration. At some time, you will that the structure will come back to the original position. So what essentially say that there is something internal mechanism there which release the mechanical energy in the structure. Many times it's through the energy being converted to the heat. If you try to see that any let's say, again simple, take the steel bar. If you take that steel bar and bend it up and down continuously and a little faster rate, you will see that at some time in a particular area, you will find that area is heated up. Essentially, so whatever the force or displacement you are applying kind of energy is being dissipated by the heat energy. So that's why inherently your material has some damping. Okay, mostly these damping are modeled as the Coulomb damping or the viscous damping or the hysteretic damping. So the most of the examples of this damping is the material damping. For example, like you have aggregates and the cement, and you apply some force, so there will be friction between the constituents. So it's essentially inherently you get the damping in the materials. You have some joints where there's some friction. So due to that friction, it resists the force and it reduces the vibrations also. You may have some kind of specific material, like for example, the viscoelastic materials, which provides the dissipation of the energy. So it's most of the time you call as the loss of energy. So it also used as for one of the example, your door seal, like when you use the automatic door closers. So it has some damping which actually reduce the displacement or the vibration. You may have the hydraulic based dampers, for example in your vehicles, the shock absorbers. So there are many dampers or damping devices are possible. So one, due to the impacts also, like the acoustic radiations also, like your sound, the energy transmitted to the sound. Then the structural radiation, like the transport of the vibration from one structure to another structure or one fluid to another fluid. So these are some of the examples. This is not the exhaustive list, but just to give an idea what is damping means. So if I come to the three damping, what I explained, that is called the Coulomb damping, the viscous damping, and the hysteretic damping. Coulomb damping is like if you take a mass or in a body rest on the ground, and actually you try to pull it, so you'll get some friction at the base, okay, and the weight of the structure in the friction coefficient, you will get that frictional force. So the frictional force times the displacement, you will get the energy, and that gives you the loss of the energy this is another way of providing the damping. It's called the dry friction damping or the sliding damping. Remember that this damping force is independent of the velocity of, like if you say that it's not a static force, I have a dynamic force. with some velocity there. So it's independent of velocity, but it actually initiate the direction of the friction force is dependent on the velocity. So if your velocity is in a positive direction, your friction force will be in the negative direction. Okay, so most there is no simple expression to this explain this damping, but it is usually expressed with respect to the viscous damping. So if I have a cyclic loading, let's say, so one cycle of loading, that means you take this displacement 5 mm, go back to again minus 5 mm, and then come back to 0. You will see that your friction force remains same, and then you are coming to your same displacement, you're coming to negative force, and then you have a similar force of the what you get in the positive direction. So it gives you 4 times of this area, or 4 times of this FD into X. So if you say that this is X and FD, so total area is 4 into mu into your Fn, that is your applied force. So that is how you say. What interesting, you see that the damping is also related to your energy dissipation of the system. So so the Coulomb damping is essentially the friction damping. When you go to the viscous damping means is the dissipation of the energy due to the liquid lubrication between the moving body. Let's say you have a bucket of a closed cylinder with some some kind of viscous fluid, and then you have a piston which you are actually pushing or the pulling. So you'll see that you will get some resistance, and that so when that body, your piston is moving up and left to right, you will get that force which is called as the damping force, which is essentially depends on the viscosity of the fluid and the velocity. So that's why the viscous damping is dependent on the velocity of the applied motion, unlike to the Coulomb damping, which is not dependent. Okay, the velocity only governs in the or only give you the direction of the damping force in case of Coulomb damping, whereas your the velocity actually the damping force in the viscous damping is directly proportional to the velocity of the motion. So if you, in the previous slide, if you see that, like is the FD and X is very simple, like you have a force into displacement, you get some kind of a rectangular shape of the energy curve. Now, once you come to the viscous damping, your damping force is proportional to your velocity. So if you see that if linear damping, will get the linear behavior of the velocity versus the force. But if I try to plot it, the force versus displacement, what you will get is a kind of a elliptical shape rather than a rectangular shape. So since it's a force and displacement, the energy or the area enclosed in this curve is nothing but your energy loss, which is is your damping energy. So you have used this concept in your force vibration test, the free vibration test, or the analysis of a structure under free vibration case and force vibration case. So it's a free vibration case, as I said, like you start from this point, the displacement, you pull the structure and release, and you will see that it will vibrate, and each cycle you have a reduction in the amplitude. So that's why, like when you write down the equation of motion, even for a cantilever structure, let's say for the water tank, although like there is stiffness in the structure, so mx double dot plus kx equals to 0, but you also add a term called the damping force because of your material damping there. So you have the a damping force which come into picture in resisting the applied forces. So as I told you that your force at the damping force in the viscous damper is nothing but your damping coefficient C times the velocity x dot. So once you try to find out the energy which is force with distance, you will get this kind of equation. The delta N E is nothing but the energy lost for the cycle is this kind of equation, which at up to particular time, what is the total energy. Now, if you see that this is a function of your velocity, x dot. So if I have a motion which is in, let's say, a harmonic motion, I can find out, let's say, my displacement is, some amplitude of capital X and sine omega t phi. You can calculate the velocity. And if you use this velocity term here and do the integration 0 to 2 pi by omega, you will get that the total energy loss in one cycle for a viscous damper under the application of the harmonic motion is pi c omega x square. So you remember the x is the amplitude, the displacement amplitude. Okay. Unlike to your Coulomb damping, which was the 4 times mu times Fn times x, this is pi c omega x square. It is that's why you get the force displacement relationship as a kind of a square term, the parabolic term, right? So now third point is the structural damping, which is called the hysterical damping. So the hysterical damping is essentially active when in a structure or a member having some stiffness and is subjected to some kind of cyclic loading, for example, like the harmonic excitation. So if you have some kind of cyclic loading, so you can see this is loading curve. Now it's not a linear hysteretic, means it will go to the nonlinear range. So you have a nonlinearity here, then it go back to the, let's say you do the unloading, then you come back to the original position where you started. You'll see that one cycle is here. So this is based on essentially the plastic deformation of the structure or the material, and the energy loss is due to the hysteresis, material hysteresis. Either it is stress strain of the element or the force deformation of the element. Okay, so these three damping behaviors are essentially used in the development of the supplemental devices, and the many of the energy dissipation devices which I talk today is based on mostly these three components. Okay, so just to give an idea of the hysterical damping, so if you have a simple mass and the spring, remember this spring, which represents the stiffness of the structure, it is not a linear spring, it's a non-linear spring, because you have the hysterical behavior and you are trying to model the hysterical damping. So in place of only K, you have K plus K eta, which is the loss factor. J represents is the complex stiffness in this modeling of the damping. So if I actually take to simplify the process, if I take, so this is my model for the hysterical damping. If I take the equivalent structure, which where you have a viscous damper with the K, you will see that this loss factor is 2 times of your damping coefficient, which is you get from the viscous damper. So hysterical damping is always in phase with the velocity, but it is proportional to the displacement. So that's why, like in the displacement based devices, so the hysterical damping actually play an important role. So it goes, the damping is essentially in the direction of the velocity, but what is the amount of damping you are getting? It always depends on what is the inelastic deformation or the displacement of the structure or the component. Whereas the viscous damping, what I have already discussed, it goes along the direction of the velocity. It is also proportional to the velocity. That means if you increase the velocity component, the damping will increase. But that is not the case in the hysterical damping. So based on this, so you have a velocity based, you have a displacement based. So the whole idea of this, we have to control the deflection or the response of the structure. So to control the motion of the structure of a vibrating body, you have to increase the damping. Now, how to increase the damping? You increase the damping by, let's say, add some kind of mechanism which will give you the viscous damping, or the hysterical damping, or the Coulomb damping. So with this as the background, I will come to the devices which are based on this. Okay. So before I wind up these fundamentals, so just to give an idea of what is the equivalent viscous damping forces and coefficients. So we have viscous damping mechanism. The damping force will be damping coefficient in the velocity So equivalent viscous damping coefficient or the damping coefficient is nothing but your C. So your hysteretic damping, it is a function of your stiffness, the force. So that is stiffness into displacement, but it is not the elastic stiffness, it is the inelastic stiffness come into picture in the hysteretic response. So that's why it is eta times your K. And when I say that what is the equivalent viscous damping for the hysteretic damper is K eta times omega. When I come to the Coulomb damping, it is nothing but your frictional force, that is your mu into your Fn. And when I come to the equivalent viscous damping, it is essentially like, dividing the energy dissipated by friction to energy dissipated by equivalent viscous damper. So it's essentially 4 mu Fn by x divided by pi omega x square. So x is cancelled. So this term represents the equivalent viscous damping for Coulomb damping mechanism. So essentially, like if I just see what is the effect of damping on a force vibration, because your structure when is earthquake is a force vibration case. So if your frequency is low, so your your amplification, that is x is, let's say, your maximum amplitude or displacement amplitude. F is essentially the amplitude of your forcing function. So when the frequency is low, actually, so your amplification or the maximum response, normalized response with respect to the applied force is only based on the stiffness. It is 1 by K. That is called the stiffness control. When you have a high frequency, so in that case, your damping is mass control. That is 1 by omega m omega square. That is your maximum amplitude of the displacement response. And in between this, if you, in between the low and high frequency, there will be a condition where your structure frequency will be close to your applied frequency, that is called the resonance. So in that case, it is called a damping. So the damping is effective in this range. That means when it is close to or similar to the range of your resonance. So if I see the typical materials, what are which material has more damping, it is related to that eta, that is the loss factor. So if you just see that, like, is the steel, the eta, the loss factor for the material, only if I am talking the material, it is from essentially 0.0002 to close to 0.001. If you see the concrete here, it is in this range. So that means the loss factor in the concrete is higher than your steel, iron, or brass. Aluminum has a low loss factor, whereas in the metal, the lead has high loss factor. That's why if you see this, these three, aluminum, steel, and lead, are mostly used in development of the devices. Okay, so if you see in terms of absolute value, like you have any gels, like the plastic or the viscous liquid, they have high loss. So that's why, like, taking this, either the metal or the material, concrete material, building materials, or bricks, or the fluid. So those are used in development of the different plastic devices. So now the next term is the structural control. So with this as background, how we can use this knowledge to develop some mechanism so that we can prevent the collapse of the structure. We can control the acceleration response, velocity response, or displacement response. So mostly the energy dissipation in this, which are being used to control the vibration of a structure, is broadly divided into three parts. One is called the passive control, one is called the active control, one is called the semi-active control. While I will go to these three controls very briefly, my most focus will be on today is on the passive control, which is essentially one of the best effective and cost-effective, most efficient and cost-effective technique. Okay, I'll come to this. So if I just give you a broad overview of the techniques, this represents some kind of frame. It can be portal peer, or it can be superstructure to peer, it can be beam, column, anything. So it's one way is connecting. So these are the primary components, and the diagonal one is a brace or some kind of damper is connected between these 2 points. Okay, so that's why you call as this is a passive. So here you have a diagonal brace. Here you have some brace with some kind of damper. Here you have brace with some kind of viscoelastic damper. You have friction damper. You have sometimes you put the liquid columns or the liquid cylinders at the top, so that because of inherent stability, it provides the negative effect on the structure. Maybe there are some tuned mass damper, active mass dampers, hybrid mass dampers. So these are various types of the dampings or just the techniques used to control the vibration. Now, just to put it into perspective, in how they are behave in different manner. So the first thing is the passive energy dissipation. So if you see, this is the fundamental one, like you have a structure here, you apply some kind of excitation, you will get some response. That is clear. Okay, so now if with this structure I add some device where that when this structure moves, this device also moves, but they are placed in such a way that they will actually pull back the structure to some extent. Okay, so that is the concept of your passive devices. That, for example, like you have a beam column frame, you apply a steel tube and connect to the beam column joints. Then you apply lateral force. Now, when this tube was not there, now with the tube, you'll see that the structure having the tube providing a more resistance to the structure. So when this tube is there, but it comes only effective or resisting the force when you apply some lateral forces. So so that's why this is called the passive. That means it does not require any additional power to activate it. The moment you have some kind of response is automatically activated and try to bring back the structure to say smaller to reduce the response of the structure. That's why it is called as the passive devices. Active control, it's a mostly a regulated format. So you have a structure here, you apply the excitation, so and then with this structure you will give you some kind of response, right? But what you do is when you collect that response of the structure, maybe the displacement or the velocity or the acceleration, and so you can, let's say you attach some kind of displacement sensor, it will record the displacement. You attach the accelerometers, it will record the acceleration of the structure due to the earthquake or any kind of excitation. So you take the readings or you take the data from the sensors, send to the controller, and the controller will process. Let's say like you have a structure, you get the displacement 10 mm. So you take the 10 mm feedback to one of the, let's say, spring system, and so that that spring will pull back the structure from 10 mm to 8 mm or 2 mm or 4 mm. So essentially, so to pull back, that means you need some kind of jack. You need to pull back the system, and this jack, how much force it will apply, it depends on how much the response is recorded, and then you have some kind of system which should tell the jack, okay, you go and pull back the system in this negative direction or positive direction. So that is called your active system. So obviously this active system is more effective, but essentially it requires the power. Without power it cannot work, right? So this is also used in the structures. So semi-active system is essentially mostly a combination of the hybrid active system and the passive systems. The only thing here is like you have a control actuator which actually tell the passive devices to how much force to apply. Okay, so that's why it's a combination of it's a semi-active control system. Hybrid system, it is a combination of the active and the passive. The difference between semi-active and the hybrid is, so one part here is controlled by the passive, and another part is controlled by this kind of active system. So this is some kind of diagram to show that how they actually behave with when the excitation is applied. So as I said, the focus here is mostly to how the passive energy dissipation actually devices are developed and how they work. So as I said, the passive devices, they don't need any kind of power system to activate when there is a excitation. Okay, the idea is it should give you the energy dissipation and it should give you the damping. So if I see that my input energy, so my input energy is, let's say EI is the input energy coming from earthquake at the base of the structure. That is the demand coming in the structure. So you have a structure. The member has like your strain energy, which is recoverable, like that is ES. You have kinetic energy of the structure, that is EK. Then you have some inherent damping due to the material. Let's say you forget about DI and DA right now. Let's say this part comes from the damping, and then this part comes from your hysteretic energy. Now, if you have a linear structure, this probably like EH will be not there. There will be some damping due to material damping. So ES plus EK plus ED. If you have a hysteretic system, which is an inelastic system, so you have ES plus EK plus hysteretic energy coming from your inelasticity behavior, and each material has some damping. So that is called the inherent damping. And in addition to this, if I use an additional damper, let's say viscous damper, it also gives the damping. So that's why this component, it gives the inherent damping plus added damping. So when your structure will not collapse, the condition is the input energy must be equals to the right output energy. That means your output energy capacity wise, it should be higher than the demand. Okay. So for example, like if you take a simple, structure, steel, steel structure, maybe a concrete structure, you have, that like 2% or 5% damping. The same structure, if I use a simple a diagonal member with a viscous damper, the damping can increase to, let's say, 20%, 30%. So as you can see that, like, obviously it reduces the response. When the response, in the sense like displacement amplitude is reduced, the demand in the beams and columns are reduced, your beam and columns are actually damaged to lesser extent if you don't have the damping or the energy dissipation devices. So so usually, like, what we do, just to give an necessarily that all damping the devices which I'll talk, they use the viscous damper, which is more easier to understand and to visualize. You may have some damping based on the Coulomb damping, that is, let's say, friction based, or you may have the hysteretic damping, let's say, due to the yielding of the members. So those energy which is released due to friction or due to hysteresis, we can always find out the equivalent damping coefficient with respect to the viscous damping. As you know that, like, if this is the straight line, it represents the shaded area is your strain energy, and this is a something looks like you have hysteretic energy, that is, you have materials or the member are yielded. Okay. Now, if I try to find out with this area how to find out how much damping I am getting, so what I can do is I can take this energy, the area enclosed here, and I know that the viscous damping is nothing but your elliptical shape. So what essentially we find out, like, the total energy which is enclosed in this loop divided by 4 pi, because you have the ellipse. So that energy, ED by pi is essentially to represents equivalent linear part. Then 4 is like the 1/4. So ED by 4 pi is the equivalent energy in 1/4 divided by the energy which are stored by the strain energy, right? That is, it gives you. So if you can, you can calculate the area under this loop. You can find that area, divide by 4, you will get the 1 quadrant, and that divided by strain energy, you will get the damping coefficient or the damping ratio, of the structure. So even if you don't use the viscous damper or viscosity based devices, even the friction based device or the yielding based device can give you substantial damping and energy which can control the response of the structures. So based on this, so there are 2 things I said. The damping you can get from the displacement is hysteretic based or the velocity. So based on that, like the passive devices are actually classified into broadly 2 categories. One is called the displacement dependent systems. That means your damping is based on the displacement, and as we know that when the damping is based on the displacement, we call it the hysteretic damping. So that's why these dampers are called the hysteretic dampers. For example, the yielding of the metallic plates, maybe the friction dampers because it's also displacement based. So they actually provide the stiffness to the structure, and they are very, very cheap. It's easy to manufacture, and they have used many building and bridge applications. So if you see some dynamics point of view, earthquake engineering or structural dynamics point of view, we know that like we have the SA, and the T, SA by T is essentially your response spectrum. We know that there is a T, SD, and SA relation. So what we can plot is SA by SD, that is spectral acceleration versus the spectral displacement. Now you have this, the response spectrum for 5%. As we increase the damping, this acceleration values are reduced, and your curves actually keep goes down and down. So these straight lines represent the constant period or time period of the structure. Okay, let's say I have a structure here without any damper. So this dot like represent like if yes there is a structure with the SA by G is this value, let's say 0.25 or something, and SD the spectral displacement, let's say 8 inch. Okay, now you add the displacement. So what it actually sometimes increase the stiffness, but that stiffness increase depends on how we install. Okay, most of the cases the stiffness increase is not that significant. So if I say that these are any line I draw, it represent a constant stiffness. If you see this, I draw and these are the stiffness lines, that the time period lines. So as you go down and down, your time period increases. So once I install some kind of displacement based devices, so there will be a little bit increase in the stiffness, so the time period, because your mass is not going to that increase that much. So for now, but since you have a damping, so now you have, let's say here you have around 7% damping, but due to the hysteretic damping, maybe 30%. So if you see 30 or 40% line here, you can see that from this point you come to this point. Now your SA by G is nearly 0.15, and your spectral displacement is essentially, let's say, less than 5 inch. So what it shows that your system is, probably one can design very smaller earthquake force, because SA by G into your SA into your weight is your mass is your force. So one can so your force you can reduce, so you can reduce your design base shear. At the same time, due to this installation of the devices, your displacement response is reduced. Okay, so in a sense, it reduces the design base shear, or it reduces the displacement response. Now the second point is the velocity based. That means your system is dependent on the damping is based on velocity. Best example is the viscous damper. So okay, so it may or may not add the stiffness to the system. So in the similar fashion, like you have here for the same time period, like once you have additional damping, you come to this position. So whether you use the velocity dependent system or the displacement dependent systems, your shear force demand on the structure is reduced, your displacement response is reduced, and in some cases, like in case of your viscous damper, your velocity is also reduced. So there are some additional systems. Some of them I will actually discuss today. So one is the recentering devices, like you have some vibration observers, the tune mass dampers, which I'm not going to explain today. Seismic isolation is again part of your passive energy dissipation. I will discuss about briefly on the seismic isolation in this lecture. So the first part of the passive energy dissipation is devices is seismic isolation. The base isolation, right? So the basic difference between this system and other passive energy dissipation system is, in many cases, when you install the passive devices, they may or they probably they don't increase the time period that much. Okay, in many cases they make the structure stiffer. In case of the passive, the base isolation or the seismic isolation, you use a very flexible layer or the flexible system. So you can think of like you have a chain, and in between, like at the middle, you have a let's say a rubber band. Okay, so if you put it or if you apply the force, so your rubber band will expand, right? So if what you can right now probably is identify is, like for example, like you hang a steel rod from the roof and you hang a chain, maybe steel chain or something on the roof. So what I can do is, once you apply the force or the displacement to the steel rod of the free end and to the chain, you will see that in the chain where you apply some displacement, some kind of vibration, the vibration actually reduces, okay, as it goes up. So the similar concept. So it provides this, it makes the structure flexible. So that means initially, like when there is no base isolation or some isolation, your structure system as your time period was here. Once you isolate the structure from the ground, your time period increases. So what is the benefit of this? So once you increase the time period, you are probably like in the falling zone of the response spectra. So here your design base shear is here. Now your base shear you have to design at this level. That means it is not only the design base shear, your spectral acceleration is on the superstructure or the primary structure is reduced. At the same time, since you make the structure flexible, again I'm talking about the same chain. If you apply the same force on the chain to the same force on the rod, the steel rod have smaller displacement, whereas your the chain has a larger displacement, the point where you apply the force. But if you see that the vibration actually is fastly degrade as it goes to the point where it is hanging. So it's a two different things. So since your acceleration is reduced or the base force is reduced, you have to increase the displacement. That's why, like the base isolations, you have to allow the structure to move. That takes care of your displacement part. Okay, so since in addition to this, due to use of some rubber-based materials or some additional systems, it provides the it's some kind of viscous materials, let's say, or some kind of fluid-based one can use. It increase the damping. So once it is increased the damping, the forces are further reduced. Okay, so so the idea is it increases the flexibility of the structure. It attracts the smaller seismic force, and it increases the structural damping. So as a result, your main primary structure is actually not subjected to that much of displacement. Okay, so these are some of the examples I'm trying to show. Like you can see, there are some isolators are used at the base or the foundation of the structure. Here is like it's at the intermediate level, right? Some kind of stub column is here. It represents first story here, and then you have isolators here, so that your top floor is isolated from the bottom floor. Okay. So that is essentially what I was explaining. Like if I see the design terms, like this was my initial design spectra, and due to the damping, I have the reduction in the forces. Okay, or so there are a lot of variety of the isolators, like laminated rubber bearing, or the sliding bearings. So I'll just briefly go through these isolators. So in laminated rubber bearing, they are based on natural rubber or the lead plug rubber bearing. Sliding is rigid sliding or elastic sliding. Then you may use the high damping rubber bearing. Remember, the rubber is the material I showed you have the highest energy loss factor. Okay, so natural rubber, like you use some layer of rubber, and then you use in between the steel plates to increase the stiffness. So if you try to model this very much simple, is a single degree of freedom system is stiffness, and the damping comes from rubber, and then you can get this kind of energy dissipation. So the area under this curve is essentially energy. It also provides the damping. Once you go to the second part of your laminated rubber bearing, so is difference between the first one and second part is you use a lead core here. Lead core, if you see the material wise, it has a better damping coefficient, the loss factor. So it helps in damping. It also, because the lead is very, very stiff, it also increases the stiffness. Okay, so this is another isolator. The third is the sliding. It is based on mechanism of the sliding friction, that is Coulomb damping, right? So that means there are two materials, and they actually slide one over other, right? So once you get the friction, your energy dissipation or the force displacement relationship is a kind of rectangle. Okay, unlike here where you have some kind of butterfly shape. So then you have the friction pendulum. So the friction pendulum, like is similar to the friction, the sliding bearing or the sliding time isolator. The only difference is you make a concave, concave shape in such a way that, like when you actually your isolator actually due to excitation is initially it will be at this position. So when you have some kind of excitation, it will take this path, it will come to this, but you know that because of the stability, it has to come back to the origin position. So inherently, it will come back to its own position. So it provides the recentering capability of the structure. So this is also called one type of isolator. So those are essentially the based on the seismic isolation devices used. The second part of the isolation, not the isolation, the damping device I'm talking about is the friction damper. We have already discussed about how the energy is dissipated when you have the viscosity, your friction, right? So so essentially, like putting the plates and allow them to slide each other. So that is essentially the concept of the friction damper is. So if you see that this is a building, and between these diagonals there is a let's say the brace. It's a brace here. There is another brace here, and in between, so there are plates which you can see that they're actually like these are the plates and the connected bolts. So when it goes in the positive direction, like it will slide. When you go to the negative direction, it will also slide. So during the sliding force, you will get this kind of hysteretic response. So just this is another point where there is single brace at the end. People use the slotted type of this. That means you have some slotting where you allow the plate to move through the slotting. So it provides a kind of friction and gives you the energy. So the ideal system, you see the friction system, it gives you maximum energy. However, this system has a very, very limited recentering capability. That means once it actually slides and the earthquake disappears, probably you will be at this position. So you have to pull back the system to its zero position. Okay. Now the third point is your viscous damper. It's simple. Like you have a cylinder where there is a piston is allowed to move through the that field viscous liquid or viscous fluid, and due to that you get the damping force, and it's sometimes there are so many types of the viscous dampers are used. Sometimes the piston is moved and the area between the piston and the surface of the cylinder, so your fluid is allowed to pass. Sometimes there is a small hole is left where the fluid is allowed to also pass through this. So it in either case, like you will get this kind of response. See, if it is a only viscous damper, the shape is more or less similar to the friction damper. Of course, is relatively elliptical. So that means it does not have again the recentering potential. The one of the most advanced one is called the viscoelastic damper. Viscoelastic means you have a viscosity base, and at the same time you add something to provide the stiffness. So in that case, your this loop will be oriented like this in one of the diagram, right? So this is just to just see the more clarity, the cross section of that. So the chamber, then you have piston, and then the chamber is filled with the fluid, and then depending on the velocity of this movement of the piston, you get the damping forces. Okay, this is one of the application I'm trying to show you. Like this is a retaining wall of the bridge, and then you have a superstructure, and to reduce the vibration of the superstructures, so you can see there are some viscous dampers are used, and they are placed in inclined direction so that they can take care of the movement in both the axes. So these are essentially the dampers, either the seismic isolations or the viscous damper or the friction dampers. All these three systems, they don't, they can be probably like reused, in subsequent applications, except like they don't reach their ultimate limits. But we sometimes use another technique where we say that the sacrificial elements. Sacrificial element means a kind of a, in your building or in your your apartment, that is electrical connections, and from between the main source and to your electrical appliances which you use, we use some kind of system called the fuse. So those fuse means if the load is very, very high, those fuse will burn away. That will not damage. That means it will provide a kind of circuit breaker so that it will not damage your appliances. So that is called the fuse. So similar concept we use called the structural fuse, and these structural fuse are mostly based on the hysteretic damping, or that means you allow that system to go post yield. That means it's not remain elastic. It will go to the nonlinear range. That means it will go beyond the yield point. So obviously, once you go beyond the yield point, you have a residual deformations. Sometimes you reach the ultimate capacity. That means once that earthquake is gone, similar to the electrical circuit, so you have to replace with a new fuse. So same thing is you have to replace with a new passive hysteretic damping system. The best part of this is very, very easy, very, very simple, and very much cheap as compared to if you talk about the base isolation system or the viscous damping systems. Okay, so just to give you why we do this, we allow in our conventional seismic design procedure, we are accept by our structure elements to go to inelastic deformations, but without stability compromising. But in many cases that doesn't happen. So you have the permanent deformations that I have already discussed, and to control this, or to control the demolishing of the repair cost, or to prevent the demolishing of the entire structures, you need some probably like the simpler and cost effective, probably the much cheaper system. So this is I'm showing you one of the electrical fuse. So what is the advantage of this? If I see that like in my force displacement, so if there is a system, beam column system, or the pier superstructure system, this might be my force deformation pier, the structure without any system. Now, if I use the structural control, now the structural control behaves like this. Okay, passive devices like the hysteretic dampers, let's say. the structural fuse, it has some stiffness and it may behave like this. So when they both act together, the final behavior will be this. So in many cases, your strength increases, your stiffness increases. So once your stiffness is increases, your displacement is reduced, your structure is capable of taking the more seismic or lateral forces. So one of the best use of the hysteretic damper is through yielding of the metals. Metal in the sense it can be steel, it can be aluminum, it can be copper. Okay. So when I say the yielding, now if you say, so just broadly, explain you how we can utilize the metal to create the energy dissipation potential. So you take the same steel plate, let's say, you put it in the UTM and pull it. So that means you are actually pushing, applying the tensile forces. When you apply the tensile forces, you'll see that it will be linear, and then you have yield point, ultimate point, and fracture. Okay, so we call that the yielding due to axial force, and that is your axial yielding. The same plate you take and hold it from the both sides, but apply lateral force like the beam. Okay, so your plate will actually deform. You keep increasing the lateral force, you will get the initial plate will behave as a linear, and then you have a yield point. So that is the yielding due to the flexure. And if you take the plate in such a way that you apply the force intent to that plate, that is shear. So if you apply the shear force, you can get again the elastic behavior and followed by the inelastic behavior. That is called the shear. So essentially the yielding is possible in any type of loading. Like for example, it can be axial loading, it can be the flexural loading, it can be the shear loading, right? So based on that, there are so many different devices are developed. One is the steel brace, which you know that like people use when there is a need to stiffen the structure, or to support the structure, people use some kind of steel tubes. Okay, so that is called the conventional steel tubes, and some advanced one is the buckling resistant steel tubes. Then the second part is like the flexural damping, where you do the allow the yielding of the plates due to flexure, and then third is the shear. If you see this, the hysteretic damping, the response is more or less similar, and sometimes it may different. I will quickly go through these systems. So one of the cheapest system used in the structural application is the steel braces. Okay, so the concentrical steel braces. Concentric means your like this simple. It can be circular tube, hollow tube. I sections is connect from this joint to this joint, the diagonal. So that means your force is concentric at the joints, or it can be used as a double shape, inverted V or V shape. So you can see that they connected at one point. Okay, so the main problem with this is one of the cheapest system. The problem is if you actually apply the tension force, you will get the yielding. But once you apply the compressive force, you know the steel will buckle, and that is exactly happens here. So in the tension, you can see that it is actually the yielding, but in the when it goes to the compression, you will reach the buckling strength, and you know that once the member is buckled, your strength is reduced. Okay, so that happens like in real steel brace. So once you have the initially it will go to the global buckling, then the reduction in the buckling strength, you may have the local buckling, then you have the fracture, then you have the complete fracture. Remember, these are the sacrificial elements. Even if these elements actually damage completely, our structure stability will not be affected. So however, like the more the damage, more the inelastic deformation, you have higher energy dissipations. Okay, so one of the way to use it is like steel brace with the connection with the gusset plate. You can see you cannot weld this plate. It's possible to weld this brace to the beams and columns, but one of the most used technique is use the gusset plate here, so that you allow the buckling of the plate or the brace either in plane or the out plane. So what we need here is like the way it is designed. First, the brace buckling, always it will most of cases the first thing. Then it goes to the yielding. Then you allow this connection to yield. So that, see, the more number of yielding, that is more number of plastic hinges, you have more energy. Then probably like at the higher forces, your beams and column yield not reach the ultimate capacity, and then you have the brace fracture. So these are some applications you can see here. So what we need here is the more number of inelasticity activities. So this dot shows where one can expect here, and here probably like one can find out. There are some preferred configurations where used like the braces are mostly used the concentric minors. So K-type braces we don't allow in many cases. Okay, so the another option is the advanced one is the buckling resistant braces. Buckling resistant braces means, since the conventional braces are essentially like they suffer from buckling. The buckling resistant braces are the systems where you can see that you have tension yielding and the compression yielding. That means you hold the plate in a sandwich tube, so that, or some concrete, so that you can get the energy in the both sides. This is the energy distribution by conventional brace. Whereas the buckling, you can see buckling resistant BRB, you can see that you have energy, symmetrical energy behaviors. Okay, I will skip this because of this time. This typically the buckling resistant brace is a steel tube and steel plate, and it's unbonded in the concrete tube, in the steel tube filled with the concrete, but there is no connection between the plate and the concrete. Okay, so there are several types of the buckling resistant braces are developed. Okay, so one of the advanced buckling resistant brace is like, instead of using the entire buckling resistant brace, which will be very much heavier because of the concrete, you can reduce, you can combine with the conventional brace and the buckling resistant brace. Okay, so so it's called the short core BRBs. So you can see that like this is what it looks like. Some of the tests we have done, you can see that like this is the part only the BRB, and this is the part which is the steel tubes, and you can see how the energy dissipation. So you have no buckling at the compression, you have more or less similar tension and compression behavior. Okay, the another one is the lightweight BRB. That means the concrete is replaced by, so all thing is the steel. So here what the point is, this can be fabricated at the site, but in general the BRB are fabricated in the factory, but the all steel BRBs, which it can be taken to the site, and there you can directly fabricate. It's much lighter than the conventional BRBs. Some of the tests we have done, you can see that they have also shown some very good energy dissipation results. If you see the problem with the energy dissipation devices, probably like it's not a problem, probably like a disadvantage. They provide the energy, excellent energy, so they prevent your structure from the collapse. The problem is like sometimes they don't have the recentering. That means if your earthquake is gone, your building will be in the tilted position. So this is some advanced BRB where the shape memory alloy, which actually bring back the system to the original position, is used. That means you get the energy dissipation, and you at the same time at the end of the day you get the recentering potential. So probably like for the more details, probably you can go to my website and find out some more on the literature. The third part is the eccentrically BRB, the brace frames. So eccentrically brace frame means essentially like those braces are not connected at the point. You leave some kind of link here, and this part is going to damage in the earthquake. Okay, so that is what happens. Like this is the moment resisting frame, this is the CBF, and this is the EBF, that is eccentrical brace frame. So here you see that this is the portion which only goes to the inelastic deformations. Okay, there are very different ways to use this. So this is some photo I'm showing where the people use the EBFs. Okay, so this is one of the photo in Japan. So what happens, like this link element, depending on the length of this link element, it may yield in shear or it may yield in flexure. So based on that, you can see this is the same shear link, but the proportionately it is designed in such a way that the length distance the length is proportionate in such a way that like everything was in the whitewash, but you can see the all whitewash or the web is removed. That means you have the shear yielding. Similarly, and if you see the many of the test results shows that one can expect this kind of static loops in the EBF, if it is shear yielding. So one can design for the shear yielding of the links as to yield in shear, or one can also use the link to yield in flexure. You can see that this is the link which is actually yielding in the flexure. Okay, so the both flexibility is there. So based on the architectural requirement, based on the space you have, the EBFs can be designed as shorter link, which will yield in shear, or the longer link, which is yield in flexure, or maybe they can be designed as intermediate link, which is between the shear link and the flexure link. Okay, in any case, you can see the loops are very consistent. They are stable. So that shows they have very good energy dissipation and damping potential. So this is some photo I'm showing in the intermediate link. You can shear yielding here, shear yielding here, and the flexure yielding here. Okay, so of course you have to detail. You have to prevent the buckling, early buckling, by providing the stiffness. Now, as the last part of my this lecture is essentially mostly focused on the tubes. The fuses. So this is one of the earliest device which called the added damping and added stiffness. So these are the only steel plates. You can see in this shape. This shape is that, like, if one section is yielded, the entire section is yielded at the same position. They are placed in such a way that, like, they will yield in flexure, and then you will get the hysteretic loops like this. Okay, either they can be kind of X shape, or they can be triangular shape. Okay, so this is one of the example where the ADAS can be has been used, and they have shown the better energy dissipation. The second is the simple shear link. That means the only you design that your web plate is going to yield. Okay, it can be aluminum shear link, or it can be steel shear links. Okay, you can see how the energy loops are very much stable and very near to the rectangle one. Okay, that is called the shear link. The third is like combining shear yielding and flexure yielding. It's called the CEFIT, where you have the plates, steel plates, which similar to the ADAS device, and then you have a steel plate. It reduces. So the ADAS device is like you have flexure yielding. The capacity is very small, so that's why you have to use a series of plates. Whereas the shear yielding is, it provides the higher force, but the ductility is reduced. So that's why, like, this device provides a higher force and the better ductility. This is one of the loop I'm showing the tested specimen. Okay, so probably like this will show some kind of examples, like how the CEFIT actually behave. So these plates are the flexor plate, this plate are the flexor plate, this is your shear plate, and then at the end probably like you have the tearing of the plates, which provides more energy. At the end of the day, like you have to replace this and then use the new link. Okay, the next is the steel plate shear wall. So it's a thin thin plates, which concrete shear wall. Like in place of concrete shear wall, one can use the steel plates, and then the steel plates provide the they will prevent, they will buckle immediately. But the point is, once it's buckled, it will provide the tension field action. That means the plate will be stressed in these diagonals, right? So now you can see this is buckling. Now once it is buckled, so you can see the buckle shapes here. Now once it is buckled, you can see that these diagonals are extended. So it's not that due to buckling you have a strength loss. You can see the loops here, how the loops are actually widening here. Okay, and so it provides the significant energy, and it has been used in many post-earthquake applications in New Zealand and in many countries. Okay, so this is called the tension field. So once so since it's a sacrificial element, you have to remove this plate and place a new plate there without changing the entire system. So to summarize this, so essentially they are very effective in controlling the seismic response, lightweight, and the fabricate to easy. So it can be actually custom made, like based on the requirements, and it can be, the shapes can be varied. based on the architectural requirements. Just to end this, I'll just show an example applications how this passive devices can be used in concrete retrofitting of concrete structures. So this is open ground story structure which you have taken 2-story. Then what we did is, like you can see the 2-story structure here, the beams and columns. So this is filled with the infill walls. And in the next stage, what we use the SEFIT like shear and plastic flexure yielding devices. Looks like this. And then we use the dynamic loading for this system. You can see the earthquake, the El Centro earthquake has been used. And so this is essentially, actually, it shows the mostly expected behavior. There's very minor damage there. Then we wanted to see that what happens. So this is how the earthquake response is. Then finally we wanted to see that if it need to be collapsed, how it will look like, just to show that how the entire system works. You can see it's not a steel, it's a concrete building, and you can see how wide the loops are like the steel buildings. So even in the soft story buildings, which is very, very predominant in our country, you can see that this can be used as one of the best effective tools to increase the energy dissipation. And that is how the link behave in the same system. Okay, they provide the energy, they provide the damping, provide the strength, they provide the ductility, and it can be used as one of the effective retrofitting techniques in the practice. Okay, I think this is my last slide. Thank you so much. I took a little longer. You have any questions? Just to summarize this, we have already explained. If you have any questions, you can tell me. Just the last slide, just to acknowledge my students. They have done all these things, my funding agencies, faculty, colleagues, and staffs of the department, and friends and family. For more details, probably you can go to my website and find out more details on those passive devices. Yeah, thank you so much.
Thank you, Professor Sahoo. This was very, very interesting presentation that you have made on a very niche topic in earthquake engineering and technology. Though there are large number of questions asked, again, because we already have exceeded the time limit quite significantly. I am taking some questions which are asked by several of the delegates. So the first question is, when we have these kind of devices added, they are called either added devices or supplemental devices. So how do we distinguish between added devices and supplemental devices?
So, okay, so essentially they are going to be same. As I said that probably you need that, let's say you have a bridge, you need the pier, you have a superstructure. So these are the primary components. Now, if you have to, control the vibration, you have to add some additional devices. That is called the supplemental devices. Now, the question probably, like I can explain in that way that sometimes these devices, particularly the BRBs, CBFs, and EBFs, they are actually designed, not only the supplemental devices, they are actually designed to take care of the lateral loads. That means they are actually part of the system also. So during the design, so if it's a new structure and you want to use the brace frame, one can take care of that primary lateral load resisting systems. If it is a retrofitting system, obviously, like, it's clear that you are going to use the supplemental devices or there is the additional devices. But so the same system, what I'm saying is it can be used as a primary lateral load resisting system, or it can be used as a secondary lateral load resisting system or the supplemental energy dissipation devices. This is not the case for all, but yeah, some of the cases, the same devices or the same system can be used as lateral load resisting system or the supplemental systems. It's up to the designer. Yeah.
Okay. The next pertinent question is what response reduction factor R should be used in those buildings where the supplemental or added devices are introduced. In particular, if it is a base isolated structure, what should be the response reduction factor for the superstructure? And are there any codes which would specify this?
Yeah, so so I can tell that like the first question is the response reduction factor. So see, the response reduction factor is it is a function of your ductility you expect in the system and the overstrength you expect in the system. So so in that sense, one can if you expect like your ductility is going to increase substantially, to a response reduction factor, one can probably use a higher value. But in most of the cases, for example, I can take the CBF and the BRBF. The concentrically braced frame, we know there is a problem with the buckling. In the BRB, we know that there is no buckling. That means we have more energy dissipation. You have more deformability. So in the concentrically braced frames, the R value, if you see that, is smaller than the BRB value. So in BRB, like for example, if you take the 2R in the sense, it is 6 in the CBF. In the BRBF, it is 8. In EBF also, one can take 8 because they give you a stable energy dissipation. Coming to the base isolation system, based on the R values, so the different codes give you the different concept. Remember that for the superstructure, the demand is very much reduced. Now, whether you need to have your structure designed to be really elastic, that there should not be no damage at all, then R should probably one can take 1. Or probably like one can use the R equals to 1.5, which can allow probably like minor damage in the structure. So if I'm designing, let's say, hospital building, so where probably probably a very, very important building, probably I will use the R equals to 1. Now, if I'm using the general residential building, probably I can use R equals to 1.5 or something. Remember, R equals to 1.5 in that case, you might expect in the concrete building. It may not be, because most of the earthquakes have reflected the energy is not transmitting to your superstructure. The demand is very much low. But further to reduce the cost, probably one can use little higher R value, 1.5. Again, there are two different thoughts on this. People may disagree, but that is my personal opinion.
Okay, thank you, Professor Sahoo. The next question is, when we have these different devices available, then which one we should go for, which one we should select, and what is the effect of soil structure interaction, especially in the soft soil? Does it affect the choice of the damper that we will choose for a particular structure?
Yeah, so the type of devices one can use, yes, it actually depends on many factors. The primary factors are like where to install. Now, if I have the flexibility to actually go to the foundation, probably I can go for the base isolations. If I have the flexibility to use the use the outer perimeter of the structure, probably I can go for the braces. If I have to use, I don't want to disturb my outer things, probably I can use the interior one. I have to also find out the base which are effective in resisting the forces. Now, coming to the soil structure interactions, see these passive devices, what is essential, it is transferring the forces. Okay, so many cases the same foundations are used to support these passive devices. Okay, so without these passive devices, when you design a structure and you know that the subsoil or the soil structure interaction you take into account, the same thing will be valid whether you go for the using the any control techniques or not. Because or even if I am going to have my separate foundation, I have if I have to look at like the soil structure interaction condition I have taken from my building, I have to take for the same for the foundations also. Because remember that all these forces, what you are going to you have transfer to the footing or the foundations. Okay, so your foundations should be rigid, and that should not be any probably like the premature failure, the settlements. So you have to take there is no different philosophy whether I have to take the soil structure interaction in a structure with control devices or without control devices.
Okay, thank you, Professor Sahu. Now it is already 1 p.m. So we have already overshooted by half an hour. So I will have to stop here this session. However, the audience, they would have a large number of questions. So I request them to get in touch with you through email, and I have given their email to you. My thanks to you in person as well as on behalf of the Indian Society of Earthquake Technology for sparing your time for delivering this wonderful lecture today on a very advanced topic of earthquake engineering using the dampers in the structures. I also thank Professor Ravi Chakka of IIT Roorkee, Professor Srivalsa, as well as Professor T.G. Sitaram for support that they have extended. In today's session, we had at any particular time more than 400 delegates participated. To be precise, it was 405 at any particular time. Also, the number of registrations were as high as 700, and we had participation from about 10 countries in total. Most of the announcements have been made by the organizer. Professor Srivalsa has informed about how to give the feedback, where you can register your attendance, as well as when the certificates will be issued to you. So if you have any more questions, you can get back to Professor Srivalsa Kolathaya. With this, I conclude this session. Thank you, everybody, and we look forward for your participation in future ISET webinars. Thank you, one and all.
Thank you, Vasant, and thank you all of you for listening me. Thank you.